briefly explain my code. So first off, I have declared start as a long, and this is important because it's the counter, and if it was an int, it would fill up too quickly. And as a long, it can run for roughly 36 minutes. Then I'm declaring the ball rate and A1 and A2 as inputs. From there, I am having start equal to millis, and this records when the loop starts and where the loop first starts. It is analog reading A2 and A1. And then here I'm just scaling the frequency so that the potentiometer at its max is 500, and then at the minimum it is 0. And this makes it easier to control. Then I have this if statement if f is greater than 0. So this prevents division by 0. And then if it's not 0, then it will create a string and print the string to the process input. And then this is while millis minus start is less than pt, it's just going to wait. And this creates the frequency that we want.
Frequency of 75, and I am sampling it at 101. And there is an aliasing frequency, and we expect this because we are sampling at less than twice the frequency. And same goes for 142 hertz. We are sampling at less than twice the frequency, so we get an aliasing frequency. Now here with the 200, we actually get the correct output of 75, and that's expected. Same with the 500, or in my case, 494. Here, we have a frequency of 100 coming from our Nscope, and the output, when we sample at 100, we end up getting a aliasing frequency of 0. When we have a sampling frequency of 141 or 142 is what it's supposed to be, we get an aliasing frequency, and we get some frequency spillage here. Now 200 is just on the cusp of being enough, and it gives us the correct output of 100. And then 500 also gives us the correct output of 100. For 215, we get aliasing frequency for 100. Same for 142, and same for 200 now. 200 is not enough to get the correct output. And 500 is enough, we get the correct output of 215 here. For 300, none of our sampling frequencies are going to be enough, and that is consistent with the data. Here we get an aliasing frequency of almost 0, and we get 18, and 100 for 200, and 191, and none of those are the correct answer of 300. And here I have a chart with, here's the Nyquist frequency, and then the Nyquist rate for each of the values, and this would be 2FM. So if our sampling rate is less than 2FM, we're going to end up with an aliasing frequency. And these are the expected or calculated values, and then here are the ones that we were experimentally found. And I'll just go through this full chart. And then here's my calculations. So let me just start with, for f equals 75 and a sampling frequency of 142, I'm just going to set 75 equal to 71 times x, and we get an x value of 1.05, and this folds down to 0.95 on the folding table. And when I multiply that by 71, which is the Nyquist frequency for 142, I get an aliasing frequency of 67.45. And if we go back up to the chart, here 67.45, and experimentally I got about 65, and this is consistent. Let me just scroll through. Here's the rest of the work I did the same way.
So now I have a triangle wave at 100 hertz, and I have a frequency of 142, which is underneath the Nyquist frequency that we need, and we get an aliasing frequency. But if I increase this to 490, now I have the correct peak at 100. My Arduino pins A1 wired up to the middle of the potentiometer, and A2 going to the output of the Nscope, and then the potentiometer just wired to power and ground. And over here I have a square wave of 100 hertz, and I have the sampling frequency at 91, and it is creating an aliasing frequency of about 9. And then if I were to increase it by twisting the potentiometer to the right, now I'm getting an output that is correct right at 100, which is similar to what we found with the sine.